Okay, so get this. We're going deep on the compact disc,
Yeah, the CD.
like really deep. We've got a whole stack of sources here all about CDs. It's like, remember that time when CDs were the thing?
Oh, yeah.
This is like a mission to go back and figure out what made them so huge.
Well, it's pretty mind-blowing, right? At their peak, CDs were selling 1 billion units a year.
1 billion.
Like
Seriously.
1 billion.
Whoa. That's not just tech, that's a whole cultural moment.
Totally.
What did that kind of access to, like, high-quality music do to how we listen?
I mean, it changed everything. But to really get that, we've got to rewind a bit. One of the big things about CDs was the switch from analog to digital.
Right, the whole core of what a CD is.
Exactly.
But what does that even mean? Like analog versus digital?
It's kind of like, imagine drawing a picture.
Okay.
You could do it with one line, right? Continuous, no breaks.
Yeah.
That's analog. But digital is like if you drew that same picture, but pixel by pixel.
Okay, I can see it.
So think about like recording barometric pressure out in Antarctica or something.
Yeah.
With an analog system, you might have a pen, right? And it's hooked to a barometer, so it's drawing the pressure on this roll of paper.
So you get this line that goes up and down.
Yeah, continuous line showing all the changes.
It's like a groove on a record.
Exactly, a physical imprint.
Okay, I'm with you.
Now digital, instead of that line, imagine you just take snapshots of the pressure.
At certain times.
Yeah, regular intervals, and you turn each reading into a number.
Some, not a flowing line, but like separate points of data.
Exactly. And that makes a huge difference.
How?
Or remember how a scratch on a record can cause it to skip?
Oh, yeah. The worst.
With digital, if you lose a few of those readings, a few of those data points, you can use the ones around it to kind of fill in the gaps.
Like it's more forgiving.
Yeah. And copying, too. Ever copied a cassette? Each copy gets worse. More hiss.
The worst.
But with digital, you're just copying numbers. Every copy is the same as the original.
That's huge for keeping the sound perfect.
It's like they used to say, perfect sound forever.
Right. I mean, was that just marketing hype?
Maybe a little. But it did open up a lot of possibilities. We could manipulate sound, process it in ways you just couldn't do with analog.
So how do you even get sound into that digital format in the first place?
It all starts with two things: sampling and quantization.
Sampling, quantization. Sounds complicated.
It's actually pretty cool. Imagine taking thousands of those pressure readings every second.
Wow, that's a lot.
That's sampling. Each reading captures a snapshot of the sound wave.
At that exact moment.
And how fast you take those snapshots, that's key.
Hey.
There's this thing, the sampling theorem, sometimes called the Nyquist theorem. I can never keep them straight.
Okay.
Basically, it says that if you sample at least twice as fast as the highest frequency in the sound, you can recreate the whole thing without losing anything important.
So there's like math behind it?
Oh, yes, serious math.
Making sure those high notes don't disappear.
Exactly. But we're not done yet. Sampling just gets us the shape of the sound wave at specific points. But we also need the loudness at each of those points. That's quantization.
So not just the shape, but how loud it is at each snapshot.
You got it. Quantization assigns a number to each sample, rounding the loudness to the nearest digital value.
Rounding, so it's not perfect.
Well, think of it like those old computer graphics, all blocky pixels.
Right.
The more shades of gray you have, the smoother the image looks.
High resolution, yeah.
Exactly. In audio, that means a wider range between the loudest and quietest sounds.
Makes sense. But you said rounding. Does that mean there's some loss?
There's always a little bit. It's called quantization error. A tiny difference between the original sound and the digital version.
Huh. So even digital isn't perfect.
It's unavoidable. But here's the really clever part. They came up with a technique called dither.
Dither? What's that?
Basically, they add a special kind of noise to the signal.
Wait, add noise to make it sound better.
Sounds crazy, but it works. Think of it like this. Imagine a painter using tiny dots of color for a portrait, right? Dither is like that. It smooths out the rough edges, makes the sound more pleasing.
Wow. Okay, you've officially blown my mind. So we've gone from analog to digital, we're sampling like crazy, and then adding noise to make it better.
It's more complex than it seems.
That's for sure.
Okay.
So all of that is how you get the sound, but what about the CD itself? What are we talking spec-wise?
Well, a standard CD can hold around 74 minutes of audio. You remember those days, right?
Vaguely.
120 millimeters wide, just over a millimeter thick.
Oh!
But the really wild part is how the data is stored these tiny pits, all arranged in a spiral track.
Like a microscopic groove.
Kind of. But get this, you could fit 60 laps of that CD track inside a single groove on a vinyl record.
No way. That much data on such a small thing.
Technology, right?
So how does the CD player even read that microscopic information?
It's like something out of Star Wars. They use a tiny laser beam.
A laser? Really?
Yeah. It scans the surface, and it can tell the difference between the pits and the flat areas around them.
By how the light reflects back?
Exactly. Pits scatter the light, the flat parts reflect it back strong. Those changes in light, that's the digital ones and zeros.
Wow. But what happens if you get a scratch or dust on the disc?
That's where the error correction system comes in. It's actually really clever. They use this system called CIRC. It stands for Cross-Interleave Reed-Solomon Code.
CIRC. That sounds intense.
It's like a safety net for the data. Imagine sending a message on this super fragile piece of paper, right?
Okay.
And, parts of it might get lost or damaged. So to be extra sure, it gets through. You write it multiple times, maybe even with some slight changes.
Just in case.
Exactly. That's what CRC does. It adds in extra information, spreads it around, so even if there's a scratch, the player can still figure out the original message.
That's wild. So even with damage, it can still play.
Most of the time. It's pretty impressive engineering. And remember, this is all happening in real time. The disc is spinning, the laser is reading all at once. But there's another part of the CD player we haven't even gotten to, the optical pickup system. That's where things get even more intricate.
Okay, so we've got this laser reading microscopic code, fixing errors as it goes. It's already mind-blowing. But how does it actually turn those digital ones and zeros back into music?
That's where the real magic happens. It's all about the optical pickup system.
Okay, what's that?
Imagine like a high-speed, super precise robotic arm, but tiny, like microscopically small.
I'm trying to picture this like in a factory building microchips or something.
Something like that. This system, it's got the laser that reads the data, but also these tiny motors. They're called servos.
Servos, what do they do?
They're like, think of them as the steering wheel and the gas pedal for the laser.
The steering wheel and the gas pedal. So they control where the laser goes.
Exactly. The focusing servo makes sure the laser beam stays, sharp, focused on those microscopic pits. Kind of like autofocus on a camera lens, but way faster.
Keeping it locked on target.
Exactly. Then you've got the tracking servo. That one makes sure the beam follows the spiral track perfectly, even if the disc isn't perfectly flat or if there's like vibration.
Wow, I never even thought about that. It sounds incredibly sensitive.
It is. That's why CD player designers put so much effort into minimizing vibrations. I mean, even a tiny tremor could throw the laser off track, right?
Right, it could misread the data.
Exactly. So they use these really heavy, solid chassis, almost like building a tank, to protect the mechanism inside.
No kidding. So it's like noise canceling, but for the CD player itself?
Kind of, yeah. And inside, they use all sorts of damping materials, strategically placed to absorb any vibrations.
Wow, it's amazing how much goes into it.
Oh, and some players even have direct drive motors. So the motor is connected directly to the disc, no belts or anything. That reduces any wobbling.
Wow, every little detail matters.
Absolutely. Even those little rubber feet you see on electronics.
Yeah.
Those help too. They isolate the player from vibrations coming from, your table or whatever.
It's amazing how much engineering goes into something we just take for granted.
Right. And we haven't even talked about the power supply yet. That's another big one. Any fluctuations in the power going to the player, that can mess with the sound. Introduce noise, distortion.
So it needs a clean, steady power supply.
Exactly. It's like the foundation of a house. If it's shaky, the whole thing suffers.
Makes sense. Okay, so we've got this clean power, the laser's reading perfectly, no vibrations. What happens to the digital data?
Right, because remember, it's still just ones and zeros at this point. We need to turn that back into something we can actually hear, an analog signal.
Right, back to that wiggly line.
Exactly. And that's where digital signal processing, or DSP, comes in.
DSP, that's a new one. What's that all about?
Think of it like the brains of the operation. It handles all sorts of things. Error correction, digital filtering, and finally converting that digital data back to a smooth, continuous waveform that our ears can understand.
Wow, so it's doing a lot.
It is.
What's digital filtering? Is that like cleaning up the sound?
Exactly. Imagine those old graphic equalizers with all the sliders for different frequencies.
Yeah, I've seen those.
A digital filter is like that, but way more precise. It can target very specific frequencies, remove unwanted noise or hiss that might have gotten in during recording or, transferring the music.
So it's making the sound as clean as possible.
Exactly. And unlike those old analog filters, which, used physical components that could wear out over time, a digital filter, it's all math. So it never degrades, never loses its accuracy.
That makes sense. So it's another step toward that perfect sound forever idea.
Exactly. Though achieving that is a bit more complicated, of course.
Right. But we still haven't covered how you go from these clean digital bits back to an actual sound wave, right?
That's where the digital to analog converter comes in, the DAC.
The DAC, okay. What's that do?
Big job. It takes those digital bits, the ones and zeros, and translates them back into a smoothly changing electrical signal that can then be amplified and sent to your speakers.
So it's going from like a digital connect the dots picture to a smooth curve.
That's a great way to put it. And just like with those connect the dots, the more dots you have, the more detailed and accurate the final picture. In digital audio, those dots are our samples. And the more samples you have per second, remember the sampling rate we talked about,
Okay.
the closer you get to a perfect replica of that original sound wave.
It all comes full circle.
Yeah.
But you mentioned something about different ways to do this digital to analog conversion. How does that work?
Ah, good catch. There are actually a few different approaches. One common one is called a weighted resistor network.
Weighted resistor network. It sounds complicated.
It is a bit technical, but the basic idea is that the DAC uses a bunch of tiny resistors, each one representing a different bit value. And by switching these resistors on or off, depending on the digital input, it creates a specific voltage at the output.
Okay, I'm kind of following. So the voltage, it changes depending on the digital signal.
Exactly. And that changing voltage, that's what represents the amplitude, the loudness of the audio signal at that moment.
It's like having a set of scales, and each one represents a different musical note. And the DAC is carefully adjusting the weights on each scale to recreate the melody, right?
That's a fantastic analogy. You've got it. And the more bits you have, the more precise those weights can be, which means a more accurate, more nuanced sound.
Wow, that's really cool. So that's one way to do it, the resistor network. What are some of the other methods?
Another interesting approach is the integrating DAC. Instead of resistors, this one uses a capacitor and a constant current source.
A capacitor, like storing electricity.
Exactly. The digital input, it controls how long that current flows into the capacitor. The longer it flows, the higher the voltage across the capacitor. And by carefully measuring that voltage, you can create a really accurate analog signal.
So it's like filling up a container with water, and the digital signal is controlling how long the faucet stays open.
Perfect analogy. You're getting it.
Well,
And integrating DACs, they're known for their accuracy and low distortion. That's why you often find them in high-end audio equipment.
makes sense. So regardless of which technique is used, this DAC thing is doing some heavy lifting, turning those ones and zeros back into music.
It's a pretty crucial link in the chain, that's for sure.
Okay, so we've got this pristine analog signal all cleaned up and ready to go. What's the next step? Just send it straight to the speakers.
Not quite. We've got to ease it back into the real world, remember?
Oh, right, because it's still super delicate at this point.
Exactly. It's like we've carefully nurtured this little signal through a whole chain of processes. We can't just blast it out without a little prep.
Okay, so what's the final step?
It's the analog output stage. Think of it like the bridge between the CD player and your amplifier.
The bridge, so it's connecting the digital world to my speakers.
You got it. It takes that refined signal, which is still pretty weak at this point,
Yeah.
and gives it the boost it needs to actually drive your speakers.
Ah, so it's like the final amplifier.
You could say that, but it's not just about raw power. The analog output stage, it actually has a big impact on the overall sound.
Really? I thought by that point the sound was, like, set.
You'd think so, right? But different components, different designs in this stage, they can all lead to subtle changes in how the music sounds. Some might make it sound warmer, smoother, while others might emphasize detail and clarity.
Wow, so even at this last stage, there's still room for, like, sonic personality.
Absolutely. It's all about finding the right balance for the music you're listening to. Now, there's one more little thing we have to do before we send the signal on its way. De-emphasis.
De-emphasis, what's that all about?
Well, remember we talked about pre-emphasis during recording,
Yeah.
how they boost those high frequencies to reduce noise.
Yeah, to make sure the hiss stayed hidden.
Exactly. De-emphasis is like the opposite of that. We're basically undoing that boost.
So we're putting some of the noise back in.
Not exactly noise. Think of it like, taking off a pair of noise-canceling headphones.
Oh, okay. Like letting a little bit of the original ambiance back in.
That's a good way to put it. De-emphasis smooths out those high frequencies, makes sure everything is balanced and natural sounding. It's all about staying true to the original recording.
Wow, it's incredible how much detail goes into every single step.
It's a real testament to the art of audio engineering.
It really is. And after this deep dive, I don't think I'll ever listen to a CD the same way again.
I hope you hear it with new ears. It's fascinating, isn't it? peeling back the layers of technology to reveal the artistry beneath.
Absolutely. But, after learning all this, I have to admit, part of me kind of misses the simplicity of just popping in a disc and hitting play.
I know what you mean. It's easy to romanticize those days, right?
Totally. But there's something kind of magical about it, too. The way a CD player takes this digital information and transforms it into music, it feels almost alchemical.
It really does.
Yeah.
And, with all the advancements in technology these days, it's easy to forget how groundbreaking the CD was in its time.
That's true. For its time, it was like magic, perfect sound forever.
Right. Though we know it's a bit more complicated than that. But still, there's something to be said for that sense of wonder, that feeling of connection with the music.
I totally agree. It's like, yeah, we have streaming now and high-res audio, but there's something about the physicality of a CD, that feeling of ownership, that still resonates.
Absolutely. And for some people, that physical connection, that ritual of selecting a disc and carefully placing it in the player, it's all part of the experience. It's a way to slow down, to really savor the music.
I love that. It's like a mindfulness practice, but for music lovers.
Exactly.
Well, I think that's a perfect note to end on. It's been amazing taking this deep dive into the world of CDs with you.
The pleasure was all mine. It's always a joy to talk about the magic of audio.
Thanks for joining us and for sharing your expertise.
Anytime.
And for everyone listening, we'll catch you next time for another deep dive.